Well, shape is important. I mean, we saw the example of the HIV drugs where having a bonding model helps to understand what sorts of molecules are worth testing. And the same thing goes with the artificial sweeteners. We look at the shape of the natural sugar, and then we try to find something that mimics that. So understanding molecular shape is important. The Lewis model is good, but it doesn't really say anything about the shape of the molecule. So sort of piggybacking on the Lewis model is what's known as VSEPR theory, VSEPR theory, because the full name is really long. Valence shell electron pair repulsion theory. This is based on the idea that electron groups repel each other. So the electron groups around the central atom are repelling each other, and they're trying to spread out and get away from each other. It's a very simple model for molecular shapes, and it works for a lot of things. So what are electron groups? An electron group is a lone pair. Those are a pair of non-bonding electrons on a single atom. A single bond is an electron group. A double bond is an electron group. It's one electron group. A triple bond is an electron group, or a single electron. The single electron you're only going to see in one of those free radicals where you have an odd number of electrons. So it's the repulsions between electron groups on the interior atoms that determine the geometry. So in this example, here we have a central atom, and it has bonds to 3 other atoms. So we have 3 bonding pairs. Each of these is an electron group. And they're going to arrange themselves so they have as much space as possible. They're trying to get away from each other. The preferred geometry is going to have the maximum separation of electron groups. That will have the minimum energy. Because when you have 2 things that are repelling each other and you force them closer together, that's a higher potential energy situation. Lowest potential energy is where they're as far away from each other as they can get. Any questions? This definition of electron group is very important to remember. Electron, a single bond, a double bond, a triple bond, they each count as one group. Okay? A lone pair is one group. A single electron is one group. Let's look at beryllium chloride. So let's draw the Lewis structure. So we're going to have beryllium, and it's bonded to chlorine on each side. And how many valence electrons do we have to mess around with here? 2 times 7 for the chlorines is 14, and the beryllium has 2, so 16. So I've got 2, 4 already, 6, 8, 10, 12, 14, 16. Is that an okay Lewis structure?
Formal is 0.
It is, because the formal charges on those are 0. Beryllium doesn't have an octet, but beryllium does that sometimes. Remember that beryllium and boron can have incomplete octets and be okay. So to figure out the geometry of this, we're looking at the central atom and counting the number of electron groups. How many electron groups on beryllium? 2. It says there are 2 electron groups. It's the 2 single bonds. Each single bond is one group. How do 2 things get away from each other? They go to opposite sides. So you could think of children in a minivan. You could think of that ex that you really, really hate, and you're trying to go to opposite sides of the world to be as far away as possible from this hateful person, right? So these groups are repulsive to each other. How far away can we get? Yes?
What about the lone pairs?
These lone pairs, that's a good question. What about the lone pairs? These lone pairs are on the terminal atoms. So they don't have an influence on what this bond does with this bond.
So they're not even counted as groups right now?
They're not counted as groups. You look at the central atom. We're going to start out with things that have one central atom. Obviously, not all molecules are that simple. And so then we're going to look at the geometry around each of the central atoms separately. But when we're looking at beryllium, we are only looking at electrons that are directly on beryllium. Beryllium doesn't have any lone pairs here. Okay, so we're looking for maximum separation, maximum angle. This is what the balloons are for. That was 3, I only want 2. They're kind of deflating because they were blown up on Monday. Okay, so if you tie 2 balloons together, they're going to be across from each other, right? So this is what's called a linear geometry. Makes a line. So these 3 atoms, these bonds, it makes a line. And so the angle around this central atom is 180 degrees. And this has been confirmed by observing molecules like this. So linear geometry. Let's look at carbon dioxide. Okay, I think we've done the structure, Lewis structure for carbon dioxide before. When you do VSEPR theory, you need to look at the Lewis structure for the compound. You look at the central atom and ask yourself, how many electron groups are on the central atom? 2. A double bond is 1 group. There are 2 double bonds, there's 2 groups. How do 2 things get away from each other? They go to opposite sides. So this also has linear geometry. Okay. BF3. Well, this is one that we used as an example for incomplete octets. And we drew the Lewis structure like this. And boron had an incomplete octet, but it was okay with that, and all the formal charges were nice and 0. To identify the geometry here, we're going to look at the central atom and ask ourselves, how many electron groups? 3. 3 single bonds. Well, how do 3 things get away from each other? If I take these balloons and put a 3rd one in here, see if I can do that without losing any of the atoms. It's a little distorted because that one is small. They make a triangle, right? They make a triangle, but it's a flat triangle. So this is called trigonal planar because it's a triangle, but it's in a plane. Oh, that's small. It's really bothering me.
Does this stuff deal with orbital? Does this go back to orbital?
Not really, no. Doesn't really. Yeah. Okay, so the angle on this one is 120 because in a plane you have 360 degrees in a circle and it's divided in 3. So they've each got 120 degrees of separation. Formaldehyde. Here's the Lewis structure for formaldehyde. How many groups are on the central atom? 3 groups. A double bond is 1 group. Okay? A double bond is 1 group because a double bond, you can see it a little better in this picture, these 2 electrons are shared between the oxygen and the carbon. They can't get away from each other. They're between the same 2 atoms. They can't spread apart. I have some model kits we can look at too, and it can't separate. So the double bond is a group, and each of the single bonds is a group. Again, 3 things getting away from each other. Trigonal planar. But in this molecule, the angles are not all 120 degrees. And that's because different types of electron groups exert slightly different repulsions. So this double bond is a little more repulsive to the single bond than the single bond is to the other single bond. And so these two hydrogens will get pushed a little bit together, and there'll be a little bit more space over here. So it's the same geometry. Trigonal planar, the bond angles are a little bit different. Okay? Yes?
So, like a double bond would have a higher
Repulsion.
And so like a triple bond would have a higher than a double bond.
Yeah. So I think the easiest way to think of this is that the double bond takes up more space. And so the double bond needs a little more space, and so these guys are going to get squished together a little bit. There's other factors involved too, but you do not need to memorize the angles for this particular molecule. If I asked you what they were, though, you should be able to tell me that the angle between the double bond and the single bond is greater than 120, and that the angle between the two single bonds is less than 120. You don't need to know how much, okay? What if we have four groups? Oh, it came apart. Go behind the screen and talk to my balloons. Oh, it didn't come apart, it broke. Always a problem with balloons, they tend to pop. This is more difficult than it looks, by the way. Oh my goodness. I'm going to pause this, because this is embarrassing. So when you have four groups, it becomes a little more difficult to visualize. So here on this slide we have the two groups and the three groups. And remember that the balloons are representing electron groups, not necessarily atoms, because a lone pair can be a group as well. When we put a fourth balloon in there, it distorts that trigonal planar shape. It pushes those guys a little closer together and makes a shape that we're generally not familiar with. It's called a tetrahedron. Okay? So the tetrahedron is a three-dimensional shape that has four corners. A cube has 6 corners, but all the angles are equal. And so you take this three-dimensional sphere and divide it into 4 pieces, and you get this tetrahedron. It's also a trigonal pyramid because it's a pyramid with a triangle as the base instead of a square. Okay? The angles here are 109.5. You should know that number, 109.5. Any questions? So if we look at methane, CH4, here's the Lewis structure. Around the central atom, we have 4 groups. 4 things get away from each other by forming a tetrahedron. And so we see that there's 109.5 degree bond angles. I just want to point out the Lewis structure looks flat, doesn't it? In this flat Lewis structure, what's that angle? 90 degrees. But it's not a flat molecule with 90 degree angles. It's shaped like a tetrahedron, and the angles are 109.5. By popping into 3 dimensions, it can increase the bond angles, which reduces the energy because of the repulsions. Any questions? If we have 5 groups, I'm frustrated with those balloons, so I'm not going to make this. And we also have a picture here now. If you take that tetrahedron and add another balloon to it, you get this shape. This is called a trigonal bipyramid. So these 3 balloons are forming a triangle. So that's that planar, triangle planar. But now you have a balloon on top and a balloon on the bottom. In this structure, not all of the angles are the same. They can't be. You just can't make them the same. So you have these balloons. These are called equatorial balloons. So if you look at this as the world, the Earth, and the globe, these balloons are around the equator, and these balloons are at the North and the South Pole. Those are called the axial position, and these balloons around the middle are called equatorial. So I'll get some models out and make some models like this that you could look at in lab, because there's nothing like just being able to manipulate it with your hands. So this is what this phosphorus pentachloride would look like if we made a ball and stick model. So in the equatorial position, we have 120 degree angles, and between the axial and the equatorial is 90 degrees. Yes?
But that would change if you had, instead of having all chlorines, you had another molecule?
If we put something else in here, or if we had a double bond, that would skew the other angles, yes.
But that's like standard form right there.
Yeah, this is where all of them are equal, and so this is as equal in terms of bond angles as you can get. So that's 5 groups. If you have 6 groups, you get what's called an octahedral geometry. So this makes an octahedron. It's got 8 sides. In the octahedron, you have 4 in the axial, 4 in the equatorial, and 2 in the axial, and now you do have equal bond angles of 90 degrees in each of them. Any questions? So let's determine the molecular geometry of carbon tetrachloride. You start by drawing the Lewis structure. So I'm going to connect the chlorines to the carbon. And I've got 4 electrons from carbon and 4 times 7 from the chlorines. 4 times 7 is 28, and the 4 is 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Is that a good Lewis structure? Yep. 0 formal charges, obeys the octet rule, very nice. How many electron groups are around the central atom? 4. How do 4 things get away from each other? They make a tetrahedron. So the geometry here is tetrahedral. Tetra is the prefix that means 4. It's that shape. Any questions?